Dear colleagues, it is a pleasure to welcome you to the Al-Khwarizmi Applied Mathematics webinar and to introduce today's speaker, Dr. Federico Sau. Dr. Sau is a mathematician whose research lies at the intersection of probability theory, statistical physics, and analysis. His work focuses in stochastic interacting systems and on understanding the large-scale behavior of complex random processes with strong connections to both theoretical and applied mathematics. He is currently a tenure-track assistant professor at the University of Milan within the Department of Mathematics. Prior to this position, he served as an assistant professor at the University of Trieste, and before that as Lies Mentor postdoctoral fellow at the Institute of Science and Technology, Austria, where he worked in the research group of Professor Jan Maas. Dr. Sau earned his PhD from TU Delft under the supervision of Professor Frank Riddick. He has also been visiting research at IMPA during the fall semesters of 2022 and 2024, reflecting the international recognition of his work. His research has been published in leading journals as the Annals of Probability and the Annals of Applied Probability, and his contributions play an important role in modern probability and statistical physics. We are very pleased to have him with us today and look forward to his talk. Please join me in welcoming Dr. Federico Sau, and please, you can start.
Thank you very much, Rafik, for the very nice and long introduction. And it's a pleasure to speak at this seminar. And today I'm going to speak about essentially these two keywords, spectral gap and stochastic exchange models. Yeah, so these are going to be the two main characters of today's talk. Spectral gap, I guess many of you know what it is. I will go through the definition in a second. And the stochastic exchange models refers to a specific type of Markov process, which we will denote by eta t. And as you will see, it's defined on some graph. And these are some examples to keep in mind. It's a large class of models, and these are just specific examples of this large class. In this class also, we encounter the exclusion process, for which the spectral gap has been determined around 15 years ago in a very influential paper by Caputo, Liggett, and Richthammer. And this has been the, let's say, the leading motivation, underlying motivation for these works I've done in collaboration with Kim and Matteo Quattropani, as I mentioned in the previous slide. And we're going to see how some other models will enter into the game. But okay, let's keep this for later. And let's go to the definition. And instead of keeping for now, like to be super general, I want to restrict to a specific model, the so-called Kipnis-Marchioro-Presutti model, the KMP model. And yeah, I forgot to say, please interrupt if you have any questions. I'm happy to stop and answer anything if I can. And so, okay, for this model, we need, first of all, to introduce an ambient space, let's call it ambient space, which is just a graph, a connected graph with a finite number of vertices. And these vertices are connected with edge weights, which are these symmetric conductances. So these weights are symmetric. We denote them by CXY, and each vertex is attached, we attach a positive weight, alpha x. Okay, once we have this geometry, underlying geometry, we
what kind of a graph you use? Any graph?
Yeah.
Or?
Yeah, so the point of the talk is to prove some results on arbitrary graphs. So, okay, for pictures, now I put a segment, but okay, think of it as an arbitrary connected graph with some weights on edges and on sides. Okay.
Okay.
And so for any finite graph, you put on each vertex some non-negative masses, which are these eta of x, and then you run the dynamics, which is simple. It consists just of two steps. First, okay, with the edge weight you gave, this cxy, you wait for an exponential clock of this rate to ring. And when this exponential clock rings, you draw, independently of anything else, a beta random variable with the parameters alpha of x, alpha y, if the edge xy is rung. Okay, here I just record the beta random variable is a generalization of a uniform random variable, uniform when the alphas are all equal to 1. But the alpha can be any positive value, and you essentially a random fraction between 0 and 1 sample with this distribution. And then you use this information to do the update of the masses. So you go from eta x, eta y to taking all the mass together you had on this edge, a fraction u, you give it to x, and the remaining fraction you give it to y. Okay? This is the dynamics that we of the, let's say, main model that I will focus on this in this talk. So just to be sure, yeah.
Please, can you recall what was eta x and eta y? You have defined them, I think.
Yeah. So is let's say if we start time zero from some masses, so are these red masses here? So this is site x. Okay, this is 0. This is y. This is eta y. This red height, the height of the.
Okay, they are deterministic.
Yeah. Initially, think of them as deterministic, and then we do these random updates.
Okay.
And so after one update, since both the location and the fraction is random, we will see some random distribution of masses.
Okay.
And then we keep doing this over time, and we will see some moving mass on our graph. Okay. And just to be sure that, okay, we're on the same page, here there's also a cartoon of this update. This is eta of x, this is eta y. We can split by using the same u in two parts, both of them. Let's say the bottom part of x by u, and then the remaining one by 1 plus u, and vice versa with the y. And then we exchange. So the top part goes to the top part, and the top part goes to the other side. And so the new configuration after one update of involving the edge xy will give rise to this new mass configuration. So this is a model, and okay, there are many questions that one could ask about this model. The one that we are interested in is what happens in the long run as time goes to infinity. What's the equilibrium? This will be like the first simple question that we can answer. And but most importantly, why the spectral gap is useful is to determine convergence rates for this model. And the spectral gap will enter into this question. And then, okay, later on, we will try to see also what about other type of exchange dynamics and what can we say about these other type of exchange dynamics. So please interrupt anytime if you have questions. Otherwise, let me go on by saying, okay, it's a matter of fact, this model is it's called Kipnis-Marchioro-Presutti because it was introduced in the 80s. So, okay, many things are known, and all this slide is about known facts. And the first one is that we know explicitly what are some invariant measures. And actually, we know that these invariant measures are not only but also reversible, and they have a specific product structure. So for any parameter rho, if you take a product of gamma gamma random variables with parameters alpha x, which depends on the site, and the scale parameter rho, then these are reversible. But okay, since we have a conservative dynamics, so at each update, when we do this redistribution, we are not destroying the total mass of the system, we are keeping it conserved. Clearly, these product measures cannot be ergodic. So it will make sense if we want to study convergence to equilibrium and to restrict to the ergodic components of the process to, let's say, fix an initial total mass. Let's say, without loss of generality, we fix the total mass to be 1. So we are really looking at probability distributions now on the set or on the set of vertices of the graph. And okay, all the rates do not really depend on the total mass, so we can restrict without loss of generality this probability simplex. And when we look at the invariant measure now restricted to this probability simplex, it's well known that if you take a product of gammas and you condition the total mass to be something, then these ratios are just the dirichlet distribution. And we have n components of these n product of gammas, and so we have a dirichlet distribution with n parameters, which are these alpha. Okay, we lose the dependence on rho, of course, because we are conditioning. And this will be the unique invariant reversible measure for the system, for the KMP model. Okay, and this is just in mathematics what I've told you so far. It has a very explicit formulas for this measure, but we are not going to use this for the rest of the talk. So going back, so once we have identified, let's say, the unique invariant measure, we, by general theorems, we know that as time goes to infinity, starting from any probability, from any initial condition, which is supported on this probability simplex, we will converge as time goes to infinity to this invariant measure. And again, going back to the same question, what about quantifying this convergence? And there are many ways to do this, through mixing times, functional inequalities, in particular, spectral gap or Poincare inequality. So maybe if you are more from analysis, this is one way to quantify this convergence. In which sense? So one of the ways in which this is true is that the spectral gap, in particular, okay, we are speaking about the KMP model, you should think of it as the best constant of the best exponential contraction rate in some L2 norm, for instance, L2 norm with respect to the invariant measure of your observables. Okay, for all observables, if you look at long times, the exponential contraction rate is the spectral gap of these observables with respect to their expectation with respect to the equilibrium. Okay, and so this best constant is what we refer to through the notation gap G alpha. Just remember that we have the KMP, but on the graph G with weights alpha. Okay, and since we are in a context of an ergodic macroprocess, the spectral gap is positive. So this is the first basic fact that we need. The second fact is that it has also, the spectral gap carries this name because it has also like interpretation in terms of eigenvalues of what? Of the negative of the infinitesimal generator of the process. And yeah, it's the smallest non-zero of these eigenvalues. So 0 is always there, and the first one, which is not 0, is the spectral gap. And also, okay, there are also operational formulations of spectral gaps in terms of minimization of energies and visual forms. Okay. I leave this for you if you're interested. These are basic facts, let's say, in analysis and probability. We will not need it, so that's why I don't insist on this definition. But the core of what our question is to understand the dependence of the spectral gap on the geometry. on the underlying geometry. So we have this model, this stochastic change model, the KMP, and okay, we want to understand if we change the underlying geometry, how does, in a quantitative way, change the convergence to equilibrium, and through the spectral graph. So before giving you the result, I quickly scan through some background, which also presents a bit this model. So as I said, this KMP model was introduced in the 80s by Kipnis-Marchioro-Presutti on the segment, so the geometry represented at the very beginning, in which, okay, there was this exchange of masses through the segment, but there was also some reservoirs at the two ends of the segment, which had the role of injecting and absorbing mass, so to create a sort of current. And this was a model to study some non-equilibrium statistical physics and try to derive some Fourier law and some important laws in statistical physics out of equilibrium. And yeah, and the model considered there is just by using the flat, let's say the flat betas, so the uniform splitting with all the alphas equal to 1. But more recently, okay, this model was reinterpreted in this sense of convergence to equilibrium by Caputo-Labelle by looking at the mixing times, again on the segment without reservoirs, but this time not just alpha is equal to 1, but all alpha constant larger or equal than 1. And but actually this model has a relative which goes back even farther than Kipnis-Marchioro-Presutti, because, okay, if you are maybe more familiar with propagation of chaos and theory, Katz in the 50s presented a sort of toy model to study properties of the Boltzmann equations, in which there was an ideal gas of particles having momentum, and they were colliding at some random time with no geometry in an infield type of situation. And after collision, this geometry, these velocities were scattered according to some random distribution of their velocities or their momenta. And if you look at this model in which you do this uniform scattering of velocities, and you look at energies, so the squares of the momenta, these squares are nothing but a version of the KMP with the parameter alpha all equal to 1 alpha. Okay, this is just maybe useful for some of you who are familiar with the Katz work. So it has many relatives. It appears in many instances. And actually, okay, the motivation for Katz to study this Katz work was to try to understand the spectral gap of Katz work, and especially, okay, after normalizing the global collision rate, was asking whether this gap had any chance to remain uniformly bounded away from zero and uniformly over the size or the number of particles. And this question was important in the Katz program to say something about the Boltzmann equation, the limit, the mean field limit of this. But this question actually, okay, took a lot of time to be answered. And only almost 50 years later, this spectral gap proof was solved by Jean Fraisse, and a few years later by impressive work by Carlo Carvalho and Loss, and also by Caputo, in which, okay, they can just prove that in the mean field case, so on the complete graph, so in our language of arbitrary graph, this G is nothing but the complete graph. We have an explicit formula for the spectral gap. As you can see, is uniformly bounded away from zero if uniformly in N. Okay, it will depend only on these alphas, all constant. And yeah, what's important for us is that, okay, not only the spectral gap, but also if you want to understand what is the statistics, the observable, which converges to equilibrium the slowest as possible. So according to really the exponential decay of the spectral gap. And it comes out of these last works that I said that these worst case statistics are quadratic in the energies. So if you take something like this, like the energy squared up to some recentering, then these are really the slowest statistics of this model. And this will be important for later on. So this was the complete graph, the mean field case. But actually, okay, the recent works by Caputo and Belacqua also managed to study the spectral gap on the segment for the same model. On the segment means only that not everybody can exchange with anybody else, but only the nearest neighbors. And they proved that the spectral gap is also very explicit, 1 over this number. Okay, it's not very important. But what's important for us is that also Caputo and Belacqua can recognize the slowest statistics for this model in this specific geometry. And this statistics is something explicit and it's linear in the energies. Okay, it's this function here up to recentering and normalization. And this thing is true for all the alphas larger or equal than 1 or constant, and it's also similar results are also known for kind of slowly varying alphas, like in a monotone way, in this recent work by Labbe and Petit. And but what's interesting is that, okay, I giving you some history of this spectral gap for the KMP. I mentioned 2 specific geometries, so the complete graph and the segment. In these 2 cases, as you can imagine, there are many symmetries, and you can actually do computation, explicit computation, and really say, okay, the spectral gap is this number, which depends just on alpha and n in this specific way. It's very explicit. So as you can imagine, if you run away from these very special graphs, you just look at any arbitrary graph you imagine, any alpha, since you need to solve an eigenvalue problem, an eigenvalue equation, in general, there is no chance to get anything explicit. And so, okay, if you want to study this problem for general graphs, there's no hope for explicit values, but there is a hope for reduction, spatial reduction, in the sense that, okay, we can say, okay, maybe not exactly the spectral gap is this number, but I know that the worst statistics are linear or quadratic. And maybe on these smaller spaces, I can, so on these very much less small number of observables, I can do some bounds. So this is an important reduction that one can do. And so this is essentially the essence of our main result, which says, okay, if you consider a graph, any graph, with some conductances, some edge weights, and some site weights, then the spectral gap of the KMP, you can always bound it above and below by the spectral gap, let's say, attained by linear statistics. This gap 1 stands for just linear statistics for the KMP. In the upper bound and the lower bound, but in the lower bound, we need to put an extra multiplicative factor, which is this gamma. Okay, which is very explicit. It's something which depends very explicitly on the alphas, and a bit also on the geometry, just because here you can minimize just over the edges of your graph. And actually, okay, if you think about even an intuitive way about spectral gap, okay, the upper bound is surely not surprising because, okay, the spectral gap should be the worst case exponential contraction rate for all the observables. And if you just take the linear ones, of course, you obtain an upper bound. But what is really the main result is the lower bound. So, okay, interesting to put them together just to really see, compare them with the same object at this multiplicative factor. Also, a property that you can check immediately is that this gamma is always between 0 and 1. And the interesting also fact is just with the 2 examples I gave you, you can see that, okay, this upper bound is sharp on the segment. So on the segment, we've seen that the linear statistics were the worst ones. And it's also possible to see just by putting together, okay, the slides I gave a couple of slides ago and before, and this expression here, that also the lower bound here is matched this time on the complete graph. So for general graphs, these two bounds cannot be in general improved. Okay, so if time, check the time, I will go, so this is the main result, and I think it's interesting also to see some ideas of the proof, just to give, it's a very like, let's say, overview of the steps of the basic ideas that are behind. So we are not going to use the same approach used in the previous two specific examples of complete graph and segment, because we don't have any geometry, any symmetry that we had in geometry, but we use a general approach which is due to maybe Mufa Chen and Wang, which uses very basic ideas of couplings. But we are not going to use it to the KMP itself, but to this hidden parameter model that I'm going to explain to you in a second. So step 0 of what we're going to do is to say, okay, we have our KMP, which we can also describe through its infinitesimal generator, and this is the expression. It's not really important for what we have or what's going to happen later. Just keep in mind that, okay, an update here, we can always express it in terms of this redistribution. So it's really written in terms of this operator, R, updating x site x and y according to the fraction u. And what it's simple to observe immediately is that if you take a polynomial in the eta variables of degree at most k, you apply the generator to this polynomial, you will get again a polynomial of degree at most k. So this is very important. When you apply the infinitesimal generator to a polynomial, you're never going to increase the degree of the polynomial. So somehow this already tells you that pk, the space of polynomials of degree at most k, is an invariant set. And so if you want to start to solve an eigenvalue equation, it's very important to have such a finite dimensional invariant. And by polynomial of degree at most k, I mean something like this, like with some coefficient, which depends on the location, and then some mixed product of at most k energies, k masses. So, okay, with this simple observation, this is something which already grants that we can really reduce the problem of the spectral gap to the problem, essentially a finite dimensional problem. Because, okay, we can use these invariant subspaces to look for polynomial eigenfunctions. Since we have reversibility, so we also have a self-adjoint, well-defined generator associated L2 space. And so we will find only real eigenvalues, and the spectrum is pure point, and we have all the nice properties that we need to start to speak about some decent notion of spectral. And most importantly, we can really write the spectral gap as the worst spectral gap among the smallest non-zero eigenvalues of the generator when restricted to these polynomials of degree k. Okay, so we will only focus on polynomials, and but let's go now to what happens, what we would like to do when we have so an eigenvalue and an eigenfunction. So the eigenfunction is this f, the eigenvalue is this lambda, eigenvalue of minus L. And okay, lambda, we suppose it to be positive. And then we have this very simple chain of identities and inequalities, which I'm going to explain. So if we want to write this, e to the minus lambda t f of eta, by the property of being an eigenfunction of the generator with this eigenvalue, this is just the semigroup applied to this eigenfunction. But since we assumed a non-zero eigenvalue, so this eigenfunction set mean zero, and mu is also an invariant measure for the semigroup. So this is we can add without any problem this expression here, which is zero. But then, okay, it's useful to add it because then we can bound this expression now by taking some sort of difference between st started at theta and let's say expectation of f times t of the process when starting from eta and from eta prime, and then taking some average over the initial condition. And so the goal is to, if you want to bound from below lambda, the eigenvalue, what we can do is to use this estimate to try to find some c and rho independent of time for which we can bound from above this expression by a constant e to the minus rho t. Okay, and then if we can do this by passing to the logs and making sure that f is trivially zero, then since to infinity we can get a lower bound of lambda in terms of this rho, of this upper bound here. Okay, this is really, let's say, a very basic idea of how to bound from above, from below some exponential contraction rate, by using also some very simple property of being an eigenfunction, etc., with mean zero. Okay, now the goal is to really get this estimate, is reduced to get a nice estimate of this type. And this is done in 2 steps. So typically the eigenfunction is kind of not very explicit, as we've seen, but okay, instead of looking at the eigenfunction, since we need to look sort of a difference of this type, okay, we would like to say that the eigenfunction itself has some regularity. There exists some control function, which we call d, for which we have a kind of Lipschitz continuity of this f with respect to this control function, which in general, okay, it's not a distance, but it can be something related to a distance. And we will see some examples of this type. And once we have this, once we find the control function, which is now explicit, then we want to find a Markovian coupling of 2 copies of our processes for which we can really see a contraction, a strict contraction over time of this control function, starting from any 2 initial configurations, eta and eta. Okay? So again, like if d is a distance, then this is really some Lipschitz-entity of the eigenfunction. And yeah, in the case in which this is a distance, this is nothing but a kind of best contraction, best rho, which somehow tells you about the curvature in the bus system 1/10 of the associated segment. Okay, this is just for those of you who have more maybe optimal transport interest. Okay, let's see like this strategy how it applies to special cases. One of the complete graph, and this kind of strategy was adopted by Ore 10 years ago, more or less. And so this control function was chosen to be the squared Euclidean distance. So just take 2 configurations and look at the squared Euclidean distance of these 2 vectors. And as a coupling, the most natural coupling that you can imagine is, okay, you have 2 configurations, you want them to be the KMP marginally, but you want to couple them together to stay as close as possible. So do the following: sample the same edges and the same U, the same random fractions, and do the updates for both of them with the same random, okay, with the same value. This is called grand coupling. And what is simple to see is that, okay, if you do this grand coupling and use this control function, then you get an explicit expression here of what's the infinitesimal contraction rate of this control distance with respect to the dynamics. And you get an expression that on the specific case of the complete graph, you can really rewrite especially by bounding, by rewriting this expression here, the second line, you can really write it as proportional to the Euclidean distance squared times a negative factor. And this is important because the negative factor is what gives us the contraction, okay? The multiplicative negative factor in front of this differential inequality. And yeah, here we crucially use the fact that we can rewrite the second summation thanks to the complete graph situation. We can rewrite it in this nice way because all these cxy, all these weights are all 1 over n. So just by conservation of mass, the summation rewrites like 1 over eta x minus 1 over eta x prime. Here it is. Okay. Let me maybe mention quickly that also on the segment, a similar approach has been done, but instead of, okay, again, using the grand coupling, exactly the same thing that I told you before, but instead of using the squared Euclidean distance between eta and eta prime, not doing it between eta and eta prime, but with respect to some function of eta and eta prime, which are the height functions. So if eta prime are some probability distribution on the vertices of the segment, take the cumulative distribution of these etas. And this is the good object in order to carry out the same type of analysis that I showed you in the previous slide. However, okay, this is really one dimension because, okay, in general, if you are on a general graph, you cannot really take the partition function of your, doesn't make any sense if you are not one-dimensional. And so both of these strategies do not really work on arbitrary graphs. So we need to change either the couplings or the distances if you want to get a nice bound, but no, we just use different processes, different process, and this is what is gonna come next, and I hope, okay. This is a bit the main point of the work is that there is a hidden parameter model, or the KMP, which was introduced recently by De Masi, Gabrielli, and Ferrari, and developed further by other authors, in which is very similar to the KMP, as you will see. So we still have the same graph. Now configurations are not eta, but are theta. They are just values between 0 and 1. And the dynamics is like the one of the KMP. So we use the same edges and the same U. But instead of doing the update as before, like giving U mass, U fraction of the mass to X and the remaining one to Y, we do a slightly different update. Like U theta of X plus 1 minus U theta Y. And then we do this exactly the same also for the other side. So here, I hope you can see the difference between these two updates. And okay, if you want to maybe have an idea where this different model comes from, just think of this eta and this update arising from a multiplication of a column vector with this 2 by 2 matrix. Okay. And if you do the vector matrix multiplication, you get this line. If instead you use the same matrix, but you do the multiplication with the column vector from the right of the thetas, you get this. Okay. And so in a sense, this is like a left multiplication version and a right multiplication version of the same essentially dynamics. And so essentially, okay, this somehow in turn gives also interpretation of, okay, eta is kind of, you can think of it as running in a direction of time, and theta is running in the other direction, if you want to couple these two processes together. But let me say, okay, what's important for us is that, okay, these metrics are that, okay, is essentially these metrics here, or like, okay, these more general version on any sides is a stochastic matrix, because as you can see, the sum of rows is 1, and all the entries are between 0 and 1. So these are stochastic matrices. But now we are multiplying, when we look at this theta process, we are multiplying from the right. So in particular, if we start, if we multiply with a constant configuration, this will be mapped to exactly the identity. It's again the same constant vector that will come out. And actually, these constant vectors are all the invariant states of these dynamics. Okay, it will depend a bit on how you update your system, the sequence of updates you choose. But since you are on a graph, everybody will update with each other. Eventually, so mass will spread all over the graph. The graph is connected. You will necessarily converge to a flat configuration, which is possibly random height. Okay, between 0 and 1. But so what's important is that, okay, the KMP model had this Dirichlet distribution as an invariant measure, while this hidden parameter model has a flat measure. And so you can understand convergence of this theta model as soon as you understand the fluctuations over space. So it's important this step is important in the sense that, okay, as soon as you can say that if you take any two vertices, their heights, their masses are essentially the same, then okay, you are very close to equilibrium for this theta model. And there is a way to quantify this, which is very efficient. Okay, it's again kind of L2 type of bound, and it's simply this kind of contraction estimate of the L2 norm, so of the variance of this spatial variance of this theta process. And you will, along the proof, you just do the computations, and you see that you can get an explicit rho, an explicit contraction rate of this spatial variance for this process, which really coincides with the lower bound I told you. So gamma, which multiplies cap 1. Okay, and now the goal will be to use this bound to really put it back into the KMP. And let me just say that, okay, this type of estimate does not require any coupling, because we are just controlling one single copy of our process or our theta process, and we are just checking when this theta process is flat. Okay, so there's no issue of how to couple two copies of the same process. So we skip one problem of this approach of Chen and Fang. We just need to choose the good notional control function. Okay, and now, okay, the main step is to go from this hidden parameter to the KMP. And these are, okay, I'm going to be a bit fast here, but it's just algebra essentially, because, okay, once you have an eigenfunction and eigenvalue for the KMP, you can transform it to an eigenvalue eigenfunction for an intermediate process just on K particles. And then once you have this, you construct an eigenfunction with the same eigenvalue for the theta model. There you use the bound. And then with this bound, you can go back. Since the eigenvalue was preserved, you go back to the K. Okay? And this is just algebra. I mean, I will not spend too much time on this, but it's something that can be checked with a bit of patience, and it's nothing complicated. Just the idea of, okay, essentially at the spectral level, Also, at the level of eigenfunctions, there is a natural mapping between eigenfunctions and eigenvalues of these two models. And so this is essentially what you need in order to construct the eigenfunction for the theta model. And yeah, you just use this control function, the variance that I told you before, to control the contraction of this eigenfunction, the Lipschitz sign for this eigenfunction, and then use the bound. Okay, I guess my time is almost over. Let me just say that, okay, I presented for the KMP, but okay, stochastic exchange models is a much broader family. And I presented the proof ideas quickly just for the KMP, but essentially the same ideas carry through to the whole family, to the whole class of models. And two essential ingredients that we used is the fact that, okay, we had an invariance of the space of polynomials under the action of the generator, and then we had the Markovian in the parameter model, for which we could compute an explicit contraction rate of this control function. And this was just a computation. And so with this idea, you can hook up a general stochastic exchange model in which you do updates in a slightly more general way. You don't just do like a splitting of the mass at x with the u and 1 minus u, and use the same u but reverse to do the update also at y. But you can choose another b, which is maybe independent, which is maybe strictly correlated to the u, which is maybe a deterministic function of the u. You can generalize these as you want. The important thing is that these updates are conservative, and the rates at which these updates occur, these rates are independent of the eta. So as you can see, the rates here do not really contain any information of what is your current state of the stochastic exchange of the eta. Okay, and once you have this, the same strategy carries through. Is just okay, more difficult, more cumbersome to write down, but you can really carry through. And here I list some models. For instance, okay, the KMP is u a beta and v 1 minus u. For the harmonic process, you take the same u essentially, but then you set the v to be 1, identically 1. And okay, the u is kind of a beta, but okay, must have some degeneracy, okay. And the immediate exchange model is much similar to the KMP, but instead this time the u and v are independent, okay, are two independent betas. And with all these models, the ones that are right here are all reversible with respect to the same Dirichlet distribution, and so you can carry the same analysis of spectral gap, etc. And we have a general theorem on spectral gap of these stochastic exchange models in the same form I presented to you earlier. And what is interesting is that, okay, we always have the upper bound, but also a lower bound, that one, and the factor gamma L1, the minimum between these two. And the nice thing is we also have a criterion to understand which one of these two values wins. And it's enough to check this condition. When this condition holds, then gamma L is larger than or equal to 1. And why is this important? Because when this gamma L is equal to 1, then here we have an identity. And so this means that we can identify exactly that the linear statistics are the worst ones for convergence to equilibrium. And actually, in these two examples that I showed you in the previous slides, we have some very simple condition which allow us to verify this condition, which is the smallest alpha is larger than or equal to 1, and the smallest alpha is also larger than or equal to 1 plus 2 kappa, where 2 kappa was this constant here. Okay. So for the stochastic exchange models, I'm going to conclude. So as you can see in some cases, this identity is sometimes true, but not always, especially when the alphas are very small. But actually, the situation is kind of different from what was proved for the interchange process and the symmetric exclusion process by Caputo, Likert, and Hammer. The model, the paper I mentioned in previous slides, in which they solved the spectral gap conjecture, in which they could prove that for this interchange process, this degree 1 reduction was always true. And we have a conjecture which is supported by some asymptotic analysis carried out with Sonu Kim in a previous work, that for stochastic exchange models, the true conjectures should be not gap L is equal to gap 1, but gap 2. So quadratic statistics are always linear, or quadratic statistics are always worst case for this model. And this is still open. And let me conclude with, simple, some concluding remarks on the fact that, we have also what's also in this paper, like some also condition for the existence and weakness of measures, some lower bounds which are not useful only for reversible systems, but also for non-reversible ones, etc. And also some remarks on open systems when you also let the mass interact with some external reservoirs. And there it's kind of more simple. The picture is a bit simpler, in which we always have gap L equal to gap 1. And I will conclude here, and if there is still some time for some questions, thank you very much for your attention.
Thank you for you, Federico, for this nice talk. Are there some questions, please? So I start by some questions.
Mm-hmm.
Do you expect that these techniques to extend to higher dimensional systems or more general interaction structures?
Like I had mentioned, you mean not just R-valued masses, but more general?
Yes, for example, yes.
Yes. So this is an interesting question. I would say that, when you have, it's not really relevant to have but RD should also be feasible as long as we maintain these kind of common ingredients of linearity. Okay, if we maintain these that the rates are linear, and then also we have a conservative type of update, we can do something. I guess I never tried, but it's interesting to be interesting to check if the techniques work well. Because of course, I mean, higher dimension, then it's maybe multiple conserved quantities and stuff like that. Yes.
Okay. Another question about the graph G. Your main results provides bounds on the spectral gap for general graphs. Which part of the argument is the most sensitive to the geometry of the graph?
So a priori, so the bound, the general bound is of this form. So now, I put here L, which is the generator of the process, but of course the generator contains information on the graph on which it is defined. So this bound, for instance, is useful if you have your stochastic exchange model, which is, let's say, infinite dimensional object, and but you can restrict the analysis of the spectral gap of this process to the spectral gap on the same graph of just a simple random walk. So essentially, this gap 1, this linear statistics, in the way the models are defined, reduces to just understanding, just like a simple random walk moves on the graph. And there, once you have your graph, it's much easier to study a spectral gap of a random walk. And for this, there are many techniques available in the literature.
Okay. If I'm not wrong, the distribution of U is beta in your work here. Okay. So
yeah, in the KMP, yes.
Okay.
This main.
So if we change the distribution of U by another distribution on 0, 1, so that it is not longer necessary, what can we say about the asymptotic behavior of the system?
So this is also a good point, because if for instance you look here, okay, these betas are the rates in which you choose the rates at which you choose a certain value of your fraction U. So the result holds for somehow the results hold for any choice of U. What's non-trivial is, for instance, so in order to speak about spectral graph, for instance, it's nice to have a good notion of an L2 space, of an Hilbert space on which you want to define your infinite dimensional generator, and you want to do spectral analysis of that. Well, if your infinitesimal generator is not self-adjoint, then it's kind of, the spectral analysis is more complicated. So, for instance, you would like to have a spectral self-adjoint operator, and for this you need reversibility of your dynamics, and general choices of U do not lead necessarily to reversible processes. So here, yeah, our method works to give bounds on eigenvalues, but then, okay, if you want to speak about spectrum, yeah, not necessarily the spectrum of the generator coincides with the eigenvalues just on these polynomial eigenfunctions.
Okay. Last question, maybe a general question, is if we modify the model that you studied in the following way, we fix a constant C, we call it a cutoff, and we assume that any segment or any weight remains unchanged if the length is smaller than C. It remains unchanged indefinitely. And if it is larger than C, we do the same thing that we do. What can we say about the equilibrium state of the system?
So, sorry, I missed. So, what is the condition?
The condition is
more than C?
Yes. We have a constant C.
Yes.
Anyway, larger than C can be fragmented, for example. If not, if it is less than C, it is we have
it
not.
Stays.
Yes, it is stable.
Yeah. So this is like an interesting question, which really destroys all the ingredients we use in this analysis, because
Yes.
And yeah, and it's an interesting model, and yeah, it's kind of very similar to kind of a confidence, bounded confidence threshold, and like, okay, if you're not too large, you don't want to split yourself with any other. So okay, it's
okay.
No. So the equilibrium situation is it's already hard to guess.
Okay.
I mean, it would depend on the geometry, it would depend on your initial condition in a very heavy way. So, yes.
Okay. Other questions? Sorry. Yes.
No, I mean, you asked this question because you're working on similar models, or?
Not very similar, but another model using the GitHub. Other questions, please?
Yes, possibly. Okay. So in combinatorics, there are some stuff which have a little bit of similar flavor. If you go to some expander graphs like Ramanujan graphs or walks on Kelly graphs and so on, for which people considered also this question of gaps and so on. And my question is, or also on GNP, the Erdős-Rényi model, my question is there a way to relate those different results, or is it always a case-by-case computations which has to be redone, or is it possible to predict something from the other model? Not directly bijection, but kind of asymptotic bijections or something like this.
But you mean so that we start from a stochastic exchange model?
For example, yours?
Yeah, on one of these graphs, or no?
Yes, and then you can relate it to some other types of problems, the ones that people had on the random walks on Kelly graph or something like this, to predict perhaps not exactly the same gap, but upper or lower bound or something like this.
Yeah, so okay. There are probably many answers to these questions. Like one of them is to say, okay, if for instance we can of course take so we have these stochastic exchange models defined on arbitrary graphs. One of these graphs could be an expanded graph, for instance, or could be like a GNP, like a Erdős-Rényi. And in this case, okay, you can study the stochastic exchange model on these graphs, and for the general result that we have is that, okay, you don't need to do the computations from the start, but if you just know the spectral gap of the random walk on these graphs, then you have upper and lower bounds of the spectral gap of the stochastic exchange model in terms of this gap. And so you don't need to do any specific analysis because you're looking at the KMP on the Erdős-Rényi graph or on another graph. On any graph, it will always be upper and lower bounds. Okay. I don't know if this answers the question.
Yes. So apparently there are already some works who did this. Apparently you were kind of suggesting that a lot of works possibly tackle these ideas.
So for this idea of doing a very dramatic dimension reduction. So the stochastic exchange model is kind of an infinite dimensional system, and the random walk on the graph is a finite dimensional situation, okay, of the size of the vertices of the graph. And this intuition was of, let's say, not so for there is this model that I spoke about, the interchange process. I don't know if you are familiar with, which is simply, okay, you have some different masses of, let's say, different height, and at some random time you swap the position of these masses. Okay, so in principle this is a very difficult process because I mean you need to keep track essentially. Like looking at the evolution of the permutation or random permutation on the vertices of the graph. But then Aldous had this conjecture that, okay, of this very high dimensional system, the spectral gap of this process was the same spectral gap of the random walk on the graph. So really dramatically reducing the dimension. And this was this paper of Caputo, Liggett, and Richthammer that proved that on any graph, you have this equivalence of spectral gaps. So it's a very nice reduction, very, okay, mathematically very beautiful, I believe. And I find also interesting, maybe computation, I don't know. I know less about that. And in this context of stochastic exchange models, we have something very similar, but it's a bit more higher dimensional than just interchange. So you see, there is this interesting role of linear and quadratic statistics, which, I mean, it's not just linear, it will be also quadratic, and there's still this understanding of can we really have a final statement, a final claim about the spectral graph.
Okay. Rafik was suggesting to play with the distribution. I will suggest another game, which is to play with the metric space. Alors, I can motivate a little bit this question. So, in computer science, there are some algorithms which are related to some dynamical systems. For example, related to computations of continued fraction expansions. And the cost of the algorithms is modeled by dynamic systems, and the cost will be related to a spectral gap of some matrices which are behind. So this is the work of Brigitte Vallée and so on, and related to other works by Dolgopiat and so on. One time I have seen that they needed to play with another metric space to find this gap, and then it was working, and then they were getting something. It was funny that you could play with the metric space. So question, is it also the case in some of the works that you saw that playing with the metric space, is there some type of metric space spaces for which we know that there will always be this spectral gap, but perhaps not the same or the same? Is there something known on playing with the metric space?
Yeah, well, I mean, okay. I've never seen these very general metric space results, but okay, at least in the literature of statistical physics and probability, like it's fairly classical and well understood techniques of comparisons. Like, okay, you want to understand the spectral gap of your system on a specific graph. Okay, you cannot really do it on the specific graph directly. You need to map it to, for instance, the complete graph, for which you know everything. And then by doing comparison, by doing path counting arguments, and you can really bound in your optimal way the spectral gap on your original system. For instance, this comparison method was used for the first time by Diacon Sau of Costa, I believe, to go from the spectral gap of the exclusion process on the complete graph or the Bernoulli class model to the boxes, like the segment. No? You want to go from a mean field to a segment. And then on these ideas, there are many also results in the 90s by Yao. So this is kind of a very, very developed technique that it has been used a lot. We wanted to avoid this because with these techniques, while you do this transformation, these mappings, you lose some constants. You lose some constants, but we are really interested in the constant. So, and then on our arbitrary graphs, it's kind of difficult to really imagine a mapping which would be efficient all the time from a graph to so. We had to go away from this idea, which is very useful in many contexts.
Okay, it was orthogonal approach. Okay, I see.
Yeah,
so
exactly.
I have possibly one last meta question. In fact, I was thinking that Rafik will ask something like this. So your model for me is a kind of crossing of Polya-Ernst models and fragmentation models. It's a kind of funny, and then for sure it is harder than each of them because you mix both of them. So is it some keywords that you already heard or some stuff that people used, Polya-Ernst mixed with fragmentation models to analyze the type of processes that you were considering?
So some fragmentation is behind these. So Polya-Ernst because of the distribution. Yeah, but okay, I wouldn't now immediately be able to relate a specific besides the formula they use, betas and the Dirichlet, etc.
Yeah, I cannot say if there's something which can be rigorously said making this link, but there are some striking stuff, the transition matrices, the role of the eigenvalues, the related to mixing time of processes. It smells a little bit not too far away.
Okay. Maybe I don't know if you if you have in mind some specific, because polyhedron is a huge word, some specific things which you think will connect, I would be happy to.
I don't know if Rafik, you did think a little bit on this connection already?
Sure, yes. There are some polyhedrons behind this problem.
So I was expecting that you asked this question, in fact.
Okay, nice. Nice. About fragmentation, okay, the simple thing that I can say, fragmentation, okay, it seems stupid as an answer. I mean, this procedure of splitting and then merging, of course, I mean, if you want to have something richer, you keep track of just the fragments. Okay, you put them together, but you always look at the richer process of fragments, not just the masses. And yeah, for instance, when we do mixing times, we prove mixing times for this type of models, it's very important to never lose this information, because I mean, it's important to understand an average fragment when it has reached a certain height, there's a certain number of splittings, and so it's fragmentation processes are behind these models.
Okay, thank you.
Thank you.
Thank you. Other questions? If not, I have to thank all the public to attend this session, and we have to thank also Federico for this nice talk and for the answers of the questions. And see you next week with a talk of Ayad Hafsi for the University of Saclay, Paris. Thank you.
Thank you.